Welcome, everyone. This is part 4 in our series on analysis methods in NLP. We're going to be talking about probing. This is the first of the 2 structural evaluation methods that we're going to consider. It's time to get really introspective about what our models are doing. Here's an overview of the probing idea. The core thing is that we're going to use supervised models, those are the probe models, to determine what's latently encoded in the hidden representations of our target models. This is often applied in the context of Bertology, which would be like, I have Bert as a pre-trained artifact, and I would like to understand the nature of its hidden representations. What do they latently encode? And for that, you might use probe models. Probing, as you will see, can be a source of really valuable and interesting insights, but we do need to proceed with caution on 2 major issues here. First, a very powerful probe model, since it is a supervised model, might lead you to see things that aren't really in your target model, but rather just things that your probe model has learned. And you might therefore overdiagnose latent information in your target model when in fact it's all being stored in the probe. And I'm going to offer you a technique for navigating around that issue. And the second one is that probes cannot tell us about whether the information that we identify has any causal relationship with the target model's behavior. It will be very tempting for you to say, oh, I have discovered that this representation layer includes part of speech information. And you might therefore conclude that part of speech information is important for whatever task you have set. But we can't actually make that inference. It could be that the part of speech information is simply latently encoded, but not actually especially relevant to your model's input-output behavior. Final section of this slideshow, I'm going to just talk briefly about unsupervised probes, which seek to address this first problem here, that the probe model might actually be the thing that's encoding all of this information that we claim to have discovered. And then when we talk about feature attribution methods, we'll get closer to being able to address some of these causal questions. Let's begin with the core method for probing. And just because this is a typical framing of these ideas, I've got depicted here what you might think of as a kind of generic transformer-based model where we have 3 layers with all these blocks. These maybe are the output representations from each of the transformer blocks. And you can see that I've got an input sequence coming in here. And the idea would be that we could pick some hidden representation in this model, like this middle one, H here, and decide that we're going to fit a small linear model, presumably, on that hidden representation, and see whether we can figure out whether that representation encodes some information about some task that we care about. So for example, if you wanted to figure out whether sentiment or lexical entailment was encoded at that point, you'd need a labeled data set for sentiment or entailment, and then you would fit the probe model on this representation and use that to determine the extent to which that information is encoded there. This depiction is a little bit poetical, so it's worth just walking through mechanically what you'd actually be doing. You would use this BERT model and process different examples, like for the sequence here, and get an output representation, which should be paired with some task label. And you would repeatedly do that for different inputs. You're essentially using this BERT model as an engine for creating representations that will become your feature representation matrix X paired with your labels Y. And it is this model that will be the basis for your linear probe model, this small linear model as I've identified it here. So you're kind of using BERT as an engine to create a data set that is then the input to a supervised learning problem. Another perspective would be that you're kind of using frozen BERT parameters in this case and fitting a model on top of them. It's just that instead of picking an output point, you've picked possibly one of the internal representations. And this is very general, and in fact, most often when you read about probes in the literature, they're actually sequence problems like part of speech tagging or named entity recognition, and therefore you might use an entire layer or even a set of layers as the basis for your probe model. Now, you can hear in my description there that there is a kind of interesting judgment call that you're making about whether you are probing or simply learning a new model, right? Probes, in the sense that I just presented them, are supervised models whose inputs are frozen parameters of the models that we're probing, our target models, right? This is hard to distinguish from simply fitting a supervised model as usual with some particular choice of featureization. As a result of this, it is essentially a foregone conclusion that at least some of the information that we identify with our probe is actually stored in the probe model parameters. And it's just that we provided useful input features that allow this probe to be successful. And that's the sense in which the inputs are latently encoding this information. But with the probe, we have not determined that it is truly latently there, but rather that it's a stepping stone toward a model that could be successful at this as conceived of as a supervised learning task. So those are important distinctions to keep in mind. As a result of this, more powerful probes, like deep neural networks, might find more information than simple linear models, but that's not because they're able to tease out more information from the representations themselves, but rather because the probe model now has so much more capacity for storing information about the task that you're probing for. So there are a bunch of different judgment calls here, and that's difficult. A very productive entry into this space is this really lovely paper from Hewitt and Liang, 2019, where they introduced the notion of a control task and the corresponding metric of probe selectivity. So here's the idea: a control task will be some random task with the same input-output structure as the target task that we want to use for our probing. Like, for example, for word sense classification, you might have words assigned random fixed word senses independent of their context. Or for part-of-speech tagging, instead of using the actual part-of-speech tags, you might randomly assign words to fixed tags from the same tag space. Or for parsing, it can get a little bit more nuanced, but you might have some edge assignment strategies that you kind of use semi-randomly to link different pairs of words into a kind of pseudo-parse, and that would serve as a control task for trying to surface latent actual parsing information. So those are control tasks, and then selectivity is simply the difference between your probe performance on the task and your identical probe model structure on these control tasks. And Hewitt and Liang use this to tease out what I think is a pretty clear intuition, which is that as you get more powerful probes, they simply become less selective. So along the x-axis here, we have MLP hidden units. So we have model complexity from left to right, where we have very complicated, powerful models at the right-hand side. And here we have accuracy, and we're measuring our control task in red and our actual probe task in this light blue here. And selectivity is the difference between those two. So you can see, for example, that the very weak models, the ones with 2 hidden units, have very high selectivity. Whereas by the time I have this very powerful MLP with lots of hidden units, selectivity has gone almost to 0. And it's very hard to say that you've uncovered any latent information, because even the control task is fully solvable with a model that has this much capacity. So I think what this is pushing us toward is always having control tasks as part of the picture and always reporting selectivity so that we can control for the complexity of the probe model itself. That's an important and easy practical step that will give you a clearer picture of what you've actually surfaced with your probe. That's the first issue. The second issue is just something that you should keep in mind as a theoretical fact about probing, which is that it is fundamentally limited in the sense that it cannot tell you that the information you discover has any causal impact on the model's input-output behavior. To illustrate that, I'm just going to show you a simple example that kind of proves this. So imagine over here on the left, I have a simple model that's going to take in 3 integers and sum them. So the output here will be the sum of 3 integers. Like if I put in 1, 2, 3, it will output 6. And it does that by representing each one of those integers as the single dimensional vector that just is that integer. And then we have a whole bunch of transformer-like model parameters, dense connections here that will lead us finally to the output layer. Right, so you can easily imagine that you probe this position L1 here and you find that it computes x plus y, which might be starting to reveal for you that there's some kind of tree structure to this model. Even though it was densely connected, it has learned a structured solution to the problem. And you might probe L2 and find that it computes z, and that would really lead you to think that you've got a kind of interesting tree structure with constituents for this addition problem. And that's certainly suggestive. However, here is an example of a model that shows that neither L1 nor L2 has anything to do with the model's output predictions. It is entirely that middle state that tells the complete story about the output. I'll leave you to work through the details if you choose to, but a shortcut way to see that is that the final parameters that take us from these output representations to the predictions have zeroed out the first and third positions leaving only the second one as having any kind of causal efficacy. Even though in this model, if you probe, you do indeed find that it looks like those representations perfectly encode these two pieces of information. That's a dramatic and clear, simple illustration of how a probe could get divorced from the actual causal behavior of the model. Again, something that's worth keeping in mind. And finally, to close this out, of course, for that first problem about distinguishing between probe capacity and actually latently encoded information, one response to that's developing in the literature now is to develop unsupervised probes. These would be models like these that seek to find in actual facts about the model with no additional supervision, the latent information that we hope to find. And this would come from simply doing linear transformations of the parameters and measuring distance between parameters as a way of getting a sense for what's actually there without the complications that come from having this additional supervised probe model. And finally, for much more information about probes and what we think we've learned from them and what they can tell us, I encourage you to check out this paper by Rogers et al., A Primer on Bertology. It has a large and interesting subsection entirely devoted to what probes have told us. Certainly worth a look and a great overview of this space.